when we're going through the process of configuring our ECU. And this is going to be relevant for those of you running continuously variable cam control systems as well as switched cam control systems. And there are some significant differences between the setup options for both, but we'll go through those. For the purposes of our demonstration, I will be using the Haltech Elite ESP tuning software. And of course, every tuning software is going to be a little bit different in the way they present these options and what specific options are available. But this will give you a reasonable idea of the process involved. Of course, as we move into our library of worked examples, you're going to be able to get a little bit more specific with different systems. Regardless though, what we're going to learn in this module should be applicable to the wider range of ECUs. So let's get started. We'll jump into our ESP tuning software. At the moment we're on our main tuning tab and we're looking at an ignition table, but what we're going to actually do is look at some of our setup functions. We're going to start by going to our main setup menu. Now, I'm going to start by looking at our trigger setup, and this is relevant specifically for our cam control, continuously variable cam control engines, but of course, we're going to need this done anyway, regardless of the type of engine we are tuning. So to do this, we're going to come up to our engine options, and then we're going to move across to our trigger tab, which we can see here. The trigger configuration, or the main trigger configuration, which is our trigger type, we can see here. We can select this from a drop-down menu. If we open up that menu, we can see there is a reasonably extensive selection for a wide range of engines. And this is, again, pretty common. This is what we could expect from most aftermarket ECU manufacturers. They're trying to make our job easy. So for a lot of common engines there, they've already done the hard work of decoding the trigger pattern, and once we do this, all we need to do is select that trigger pattern and everything's set for the ECU to understand the information that's coming through. In this case, our option that we are using here, as we can see, is Subaru EJ25 WRX, model year 06. So there is a little bit of variation here because we are actually running a Japanese domestic market EJ20 in this particular Subaru STI. However, what's relevant for our application here is that the trigger pattern is the same. This is a quad AVCS, which is Subaru lingo for continuously variable cam control engine. If you're ever unsure of the specific trigger mode for your particular engine, then you can always contact your ECU supplier, and they're going to be able to give you the information on what trigger mode to use for your specific engine. So we've got our main work done here. We've got our EJ25 trigger mode selected. So that's already set up our Haltech Elite to expect information that is relevant to quad variable cam control. Moving down, we have a little bit more information that we do need to set up here. And this is really more specifically around general trigger mode setup. If you need more information around this, then our practical standalone tuning course covers this in much more detail than I'm going to do here. But here for our trigger signal, our RPM input, we have the sensor type. So this is a reluctor sensor, and we can also choose the trigger edge, and we talked about this earlier in the course as well. So we've got our falling edge, which would be typical. So that's going to make sure that we aren't going to get timing drift there if our pattern is incorrect, our trigger edge is incorrect. We've also got in Haltech lingo here, the home signal, or synchronization as it's often called, and this is the engine position information. And this also gives the ECU information about the cam position for the camshaft that this particular signal is coming from. So we can see that this particular sensor is a Hall effect sensor, and we are triggering off the falling edge there. Because it is a Hall sensor, we have got the pull-up enabled, otherwise we're not going to get a valid signal from this. This setup alone should be enough to get our engine up and running. We should be getting synchronization information. We should be able to crank the engine and see RPM, and the ECU should be synchronizing properly, and that's going to confirm that we've got that information set up correctly. Now that we've got our trigger setup done, we're going to move down to our functions here in the menu structure, and we're going to look at what we would need to do to set up the rest of our cam control. So what we've got here is the cam control function. We can click on that, and that's going to give us all of the setup parameters around the cam control. If you haven't already selected cam control as a function, then you're going to need to enable that first, and you can do that by coming up and clicking on the add remove functions, and you can choose cam control and enable it. I've already done that there. So we start with our wiring tab, and we can just work through this in order. That gives us a nice sensible workflow. First of all, we've got our options here. So number of banks. Pretty straightforward here. We're running a Subaru engine, which is of course a boxer or horizontally opposed engine. So we have 2 banks of cylinders. We've selected that. Then we have our modes. So we can have intake only, exhaust only, or intake and exhaust. This is a quad variable cam control engine, so obviously intake and exhaust is what we want to select. Next, we also have the option here of number of solenoids per camshaft. It is most common that we would use 1 solenoid or actuator for a camshaft, but certain engines do use an advanced and a retard solenoid, so that will be dependent on your setup there. Let's just move this up a little bit, and we'll make the box a little bit larger so we can get a better idea of what's going on here with our wiring setup, because there are a few setups we need to go through here. So first of all, working down in order, we can see here that our intake cam 1 input, which is our cam position for our intake cam 1, where that's coming from. And we can see that that is the home input, which is what we've just looked at. In other words, our synchronization input. As I mentioned, this does 2 tasks here in the Subaru engine. It gives the ECU information about the engine position, so which particular cylinder is firing at any time, critical for sequential fuel injection and direct fire spark. But in this case, it's doubling its duties here as also giving cam position information. Now, that's not always going to be the case. Some engines provide both an engine synchronization or engine position input plus a cam position sensor. So it's just going to be specific to your engine there. We then come down to our output for that particular cylinder, or that particular camshaft, I should say, which here we can see we've got our cam 1 output, intake cam 1 output is on our injector 7 output. Again, the specifics of this will depend on the output you're using in the ECU. Most of the time there will be auxiliary outputs that you can assign for a cam control solenoid or actuator, or alternatively unused injector or ignition outputs can often be used as well. It's important to also mention here the active state. So whether the state when the solenoid is active is going to be low, that would be most common, so it's going to be switched to ground, or whether it's going to be switched high. So the way these actuators work, one side of the actuator is wired to a 12-volt supply, and then the ECU pulses the other side of the actuator to ground in order to activate it. So we move through here. We've got our intake cam 2 input, so cam position for our other intake cam. So we've got that wired up here to SPI2 on our Haltech Elite. We then need to set this up. So this again needs to be specific to the input. We have here a Hall effect style sensor triggering on our rising edge. Because it is a Hall sensor, we have our pull up enabled. The rest of the process from here is really a rinse and repeat. We can see we've also got an actuator output assigned for our intake cam 2, and then we've got the same options available for our exhaust cam 1 and exhaust cam 2 inputs and outputs. But essentially, once you've got the process down, it is just a case of assigning an input to the cam position and then assigning an actuator output for the cam solenoid. It's also worth mentioning here, as we discussed in the body of the course, particularly for a reluctor sensor, polarity is important. If you've got the option, and a lot of aftermarket standalone ECUs do these days, you can always do a trigger input capture, which is essentially a built-in oscilloscope, and that will allow you to visualize all of those cam position inputs and make sure that regardless whether you're using a reluctor input or a Hall sensor, that you're triggering on the correct edge and everything is working properly. In the Haltech Elite, we don't have the benefit of the trigger scope function, so we can't do this. We could, of course, hook up a oscilloscope to the ECU and see what those signals are doing. The other alternative, though, is with the cam control inactive, so our solenoids are disabled, what we can do is start the engine up, and we can watch what the cam position is reporting as we increase the RPM, and it should be relatively stable. That's going to give us an indication that we don't have the polarity of those reluctance sensors around the wrong way. Now that we've got our input and output set up correctly, we're going to move across to the next tab, which is our cam control tab. And this gives us the ability to control some of the high level functionality of our cam control system. So starting here, we can define the maximum rate of change of our cam target. So in this case, we see that that's set to 90 degrees per second. And this is just to try and help the mechanical system keep up with our changing cam target. And again, if we've got sensible cam targets in our map, this is going to become less of an issue. We've next up got our intake cam frequency. So again, this is going to be specific to the engine that we are tuning, the actuator. Somewhere between 200 and 300 hertz, as we've already talked about in the course, is going to be pretty typical. And you can also change that value. You can also change the frequency as you're going through your setup, particularly through the PID control setup stage, and just see if a faster or slower frequency does improve the response of your system. We then have our intake duty cycle minimum and maximum. So this essentially clamps the minimum and maximum duty cycles that will be used. Obviously you can see there 20 and 80%. Generally we're going to find that our continuously variable cam control system, when the cam is holding at a fixed angle, the actuator duty cycle is probably going to be somewhere pretty close to 50%. And it doesn't necessarily need to have a massive swing to a positive or negative value from there in order to advance and retard the cam. So basically limiting the maximum value there, maximum minimum values that the actuator can provide will help make sure that the system responds quickly. So 20 to 80%, that's going to be a pretty good place to get started. You can also monitor once you are setting up the cam control system and see what sort of minimum and maximum values the actuator is actually moving to, and that's going to again give you a good guide on where you can set these minimum and maximum values. For our intake cam here, we also have the direction of the cam movement, and typically for an intake cam, it will start at the rest position, will be the most retarded position. So we're going to be advancing from there. But exactly the same settings for our exhaust, and we can see that when we get to our exhaust cam direction, we again are starting there. The rest position is the most advanced, and we're going to be retarding from there. The Haltech also gives options around long-term trims for a lot of functionality. I'm not going to deal with that today though. It gets a little bit beyond the scope of our course in general. So at this point we've got the main aspects of our cam control system dialed in, set up in the software. In a lot of ECUs we do also need to set up the cam offsets. So this is essentially very similar to the process of dialing in our base ignition timing. What we're doing is essentially adjusting an offset parameter in the ECU so that when the cam is in fact in its most retarded position for the intake cam, for example, we are actually reading a value of 0 degrees. Likewise for the exhaust cam in the most advanced position, we're going to be recording a value of 0 degrees. So that is pretty common across the board with most aftermarket standalone ECUs that are using cam control. Haltech actually don't do it that way. Instead, what they do is calibrate the 0 position during the cranking process. So we'll close our setup down by clicking OK, and what we'll come over to is one of the tuning tabs I've set up here, which is Cam PID, and we'll be looking at this in a further practical demonstration. But for our purposes here, we've got a time graph that's showing us the cam control intake cam 1 angle versus target. Obviously it's not doing anything at the moment because our engine isn't running. The important part I want to take away from this though is we can see we've got our cam control intake 1 angle in a text box here, and it's saying calibrated at the moment. What I'll do is we'll just power our ECU up, and we've got it powered up now. I'm going to start the engine, and what you'll see is that once the engine is running, after a couple of seconds, this little box here is going to say calibrating, and basically at this point the output actuator is not operating. It's the ECU is going to know that the cam is in its most retarded position, and it's going to zero the offset at that point. It will say calibrating, and then it will read the actual value. So let's watch that process now. We'll start the engine. All right, we've got our engine up and running. You can see it started by saying calibrating, and then it's jumped to reading 0, and now our cam controller is functioning. You can see that the cam target, or the cam position I should say, is moving around a little bit, and that's pretty normal as well. Important to point out here that we haven't got our PID set up, which is why it's not tracking our current target exactly of 4 degrees, but that's the process that Haltech use. We'll shut the engine off now and continue. So at this point with a continuously variable cam control engine, we should be in a position where our inputs and outputs are set up. We've got our offsets set up if required, and we'd be in a position to actually start the rest of the tuning process. Before we finish this module though, we'll just have a quick look at some of the aspects that go into a switched cam control system, such as Honda's VTEC, just for one example. So what we'll do is we'll head back into our main setup tab, or main setup screen, and we're going to look this time at a different function which I've already enabled here, which is cam control switched. Again, different ECU manufacturers will have different terminology around this, but this is the way Haltech have done it. Again, what we'll do is we'll come across to the first tab here, which is our wiring tab. So we need to assign a output for our switch cam control actuator. And again, just like our cam solenoids, our cam control solenoids, we can typically use an auxiliary output or digital pulsed output, as Haltech refer to them, or a spare ignition or injector output. In this case, I'm using ignition 8, and again, the active state there is low. We're switching the solenoid to ground. So essentially, this is identical in terms of its setup to a continuously variable cam control actuator. Having said that though, with a switch cam system, it's not pulse width modulated, it's simply switched on or off at a particular RPM point. We also have the option here to set up our output mode. So this is just, again, totally dependent on your engine. You can see that at the moment I've got it set up to intake or shared output. We can set this up to exhaust, intake and exhaust, 2 intake outputs, etc., depending on the particular setup. So this is what we'd use here for something relatively straightforward, and it's just a single output. We also have some preconditions. So moving across here, we'll look at our preconditions tab. So we can make sure that there is no chance of this switching outside of these conditions. So in this case, we've got 3 options available. We can set a minimum vehicle speed, minimum throttle position, and a minimum coolant temperature. Really, this is up to you. If we look at the way someone like an OE manufacturer such as Honda does this, they do use some of these preconditions. So for example, you won't be able to actually enable the VTEC system with the vehicle stationary under normal circumstances. The coolant temperature is quite important because obviously this has a knock-on effect to our oil temperature. The switch cam control system is oil operated, so there may be some reasoning behind making the cam control switching not occur below a certain engine temperature. What we do need to be mindful of though is that if we are going to use these preconditions, remembering back to the discussion we've had in the body of the course, if we are using a single ignition and fuel map and we've tuned that then and optimized them for a given switchover point, if we then eliminate switchover point using some of these preconditions, we need to understand that, of course, our fueling and our ignition timing are no longer going to be optimized. Can get around that, of course, by using dual maps. The choice, of course, is up to you and what you're trying to achieve. Just need to understand the implications of those choices. Moving on, we'll get into the meat of the tuning process here, or the setup process here, which is our intake tab, and we can select here, first of all, whether we want to have an off RPM condition. Sounds a little bit confusing. Of course, we want the system to turn off, but in Haltech lingo, basically this is defining whether we are using a single point to switch the cam or whether we are switching the cam at 2 points, basically advancing the cam. Let's say we're talking about an intake cam, and then switching the system back off to retard it again higher in the RPM. So let's look at our simple system first, which would be likened to how Honda's VTEC system works. So we'll leave the off RPM condition disabled. Moving down, we can see we've got our parameters here for our cam windowing, or when we're going to switch on, versus our engine load and our engine RPM. So I've made this really simple here. We can see our minimum load here is minus 100 kPa and our maximum load is 0 kPa. In reality, we're probably going to not be at the extremes of the manifold pressure for a naturally aspirated engine, but we can choose something suitable. Maybe for our maximum load, we're going to be wanting to switch the system when we're close to full throttle, and that may be somewhere around about maybe minus 10 kPa or thereabouts. Maybe our minimum load want to be a little bit above our cruise manifold pressure. Maybe that's minus 50 or maybe minus 60 kPa or thereabouts. Again, you're going to choose settings here just relevant to your particular application. Then we've got our minimum load on RPM and our maximum load on RPM. So essentially what this simply means is that when we are at our maximum load of 0 kPa, our switchover point is going to be 4,500 RPM. When we are at our minimum load of minus 100 kPa, it's going to be pretty difficult to get to, our switchover point is going to be 5,000 RPM. Now this can be a little bit difficult to visualize, so Haltech have done the heavy lifting for us, and we have this nice little graph of load versus RPM, so we can see for any particular load point exactly where we are going to be switching. So for example here, minus 50 kPa, we can see that we're going to be switching around about 4750, maybe almost 4800 RPM. So it's a nice visual representation of how exactly that is going to work. All right, so that's our simple VTEC style system. If we were running something like Nissan's VTC, which is common on some of their SR and RB engines, we may want to switch the system on and off. We can do that by coming back to our off RPM condition, currently disabled. Of course, we're simply going to select enable there. And that then gives us this other set of parameters here, which is our minimum load off RPM and our maximum load off RPM. And again, we visually see exactly what's happening here. So if we were, for example, at our minimum load of minus 100 kPa, and we come up through here, we can see that as we increase the RPM from idle, we're going to initially switch that cam system on just below 5,000 RPM, or just at 5,000 RPM, I should say, and then we're going to switch it off at 6,500 RPM. So it makes it really easy to see visually exactly what's happening there. The system that we've just looked at here is really set up to work on a single base map inside of the Haltech Elite, and in fact Haltech don't really make it particularly easy to use a true dual map system. However, there are workarounds, and again this will depend a little bit on your specific ECU. Let's have a look at that though. What we'll do is we'll head back to our engine options, and we're on our fuel tab here. We can see that we've got a range of options for the fuel tables that we want enabled, and we can choose these options depending on the specific functionality we want in the engine. However, if we were going to try a dual map setup, one way we can do this in the Haltech Elite is to enable our generic correction. So we've actually got 4 generic correction tables here. So if we enable generic correction 1, we can see we now get a new tab up here on the right hand side that says fuel generic 1 correction. Let's click on that, and what we want to do is set up our conditions that are going to enable this. So we can click on conditions enable. You can see here that it's set to enable on RPM. Now what we want to do here instead is click on select, and we're going to type in switched cam, and that's going to give us our switch cam output status. So we'll double click on that, and that's going to then allow us to use the state of our switch cam output to drive whether our generic correction is active or not. So here we can see that set up it to be greater than, we want to select equal to, and we want to select 1. So this is only going to move between 0 when it's off and 1 when it's active. So that sets up when our correction is going to become active. We can click OK now, and when we select that, we can see that we now have generic corrections out here on the left-hand side. We'll click on that and we have our fuel Gen 1 correction. Now, it is important here to understand that this is a correction. It's applied over and above our base map. So this is a little bit of a clunky way of dealing with this. Ideally, we would have an option where we were simply using the system I've just gone through to switch completely between one fuel map and another. And of course, we'll be doing exactly the same for our ignition table. In this case, though, this will be applied as a correction over and above our base fuel table. So that's important to understand. We can see at the moment as well that the setup is relatively unusual. We've got our full throttle time on the horizontal axis, and we've got gear on the vertical axis. We can change our axes by coming up and clicking on the table axis setup, and then we can enable more suitable axis. So for example here, we'd probably replicate the axes that we are using for our main fuel table. So in this case, we would be selecting fuel load for our horizontal axis, and we would be selecting RPM for our vertical axis. We can then, once we've gone through and done this, we can then select suitable breakpoints. Again, probably replicating as well as we can the breakpoints from our main fuel table, noting that the maximum number of breakpoints here is 16 for RPM and fuel should be sufficient. We'll close that down, and we need to just talk about the way this will work. So what we would want to do if we want to use this style of system on the Haltech Elite, we would start by essentially tuning the engine in the areas we want to run with the VTEC or switch cam control system completely disabled. So from that basis, we would be doing all of our tuning here in our fuel base table, our volumetric efficiency table, and we would be dialing that in correctly. Once we've done that, we can then enable our switch cam system, get that switching, and remembering, of course, as soon as that switches, our fuel generic 1 correction will become active, and we'd simply be making adjustments to this table in the areas relevant in order to get our tuning on point. Whether you want to do this with just the fuel or the fuel and ignition is completely up to the individual. As I've mentioned, it's a slightly clunky workaround that we've got here with the Haltech. Most ECUs will give us the ability to just switch wholly between 2 fuel and 2 ignition maps. It's important to make sure that we are using the output for our switch cam control to actually function between those 2 maps. It's going to make sure that we're always on the relevant map for our particular application. So there you go, a bit of a walkthrough on some of the considerations with our ECU configuration for both continuously variable cam control systems as well as switched cam control systems.